see your screen.
Sorry. Okay. So can you see my screen?
Yep.
Okay. So thank you very much. I'm Baihua from Loughborough University, associate professor in Department of Computer Science. I'm senior member for IEEE, and today the talk is machine learning and deep learning for autonomous underwater vehicle. Sorry, I lost my sound. Okay. And so today I don't get too much into technical detail. Mainly I talk about the problem and the challenges, and also some topics we are addressing in autonomous underwater vehicle. Yeah, thank you. Okay. Yeah, so Loughborough University is at the middle of the UK. It is one of the top 10 universities in the country. We have 5-star world-class research and facility in science and engineering. It has been awarded 7 Queen's Anniversary Prize, second only to Oxford University. These days, everyone knows driverless vehicle on the ground. So today, what we are talking is the autonomous vehicle underwater, the AUV. An AUV is a robot that travels underwater without requiring the input from a human operator. In the history, remotely operated underwater vehicles are controlled and powered from surface by the human operator, where physical connections are using remote control. The first AUV is developed by the University of Washington in 1957. Compared with the driverless vehicle on the ground, underwater AUV need to work in much harder and different conditions. For example, the seas, rivers, lakes, and oceans. They all have very different surroundings. The AUV should work at different seasons, day and night, different water depths, temperature, and pressure. And they reduce the operational cost and human risk. Some of the environment is not safe for human to work. Some AUVs are bigger and some are portable. Yeah. The price can be several hundred pounds to thousands of pounds. Some AUV also human-like and attached with manipulators to complete more complex mission. There are so many applications for AUV. The oil and gas industry use AUV to make detailed maps of the seafloor, to carry out pipe survey and pipeline inspection, or to inspect underwater man-made structures. AUV is also required for marine ranching, fishing, biology research, and underwater environment. There are so many applications required AUV in military, surveillance applications, and also the air crash investigation. We also need AUV to help environment protection, search and rescue, and also hobbies and entertainment. Characteristics of the AUV. The most important is the autonomy. It means to perform target tasks without active human interactions. Tasks include high-level tasks like planning, control, and aerodiagnostic, and also low-level sensing, using sonar and camera depth sensor to sense the surroundings and deal with the lighting conditions. AUV must be able to move within the environment accurately. Movement can be ranged from small degree accurate movement for robotic arms and also large-scale free navigation. computational power is also required to process the sensor input and generate real-time commands. The design of the AUV are also from high level to low level. For example, at the high level, brain functions include navigation, path planning, curiosity, exploration, human endeavor, and then AUV interaction and cooperation of group AUVs. And also vision and perception functions like SLAM, mapping, sampling, data fusion, scene understanding, robotic vision, vision odometry, and also many automation functions, especially the kinematic and the dynamic control. On the hardware, we require the embedded devices, sensor design, and also energy supplement. It is very challenging to achieve high accuracy real-time performance with limited results on AUV. For navigation, you can't have the GPS and high frequency radio signals in underwater. We also have error accumulation problem when we use IMU for navigation. Underwater environment is unstructured, highly unstructured, and difficult to model. It's also very unpredictable due to the dynamic of the wave, current, and then the animals. Underwater has very low visibility, and blurring, and low contrast. It's difficult to use infrared cameras or do the camera calibration. We need to consider limited onboard resources, limited computational capability and memory on embedded systems, limited power supplyment. We require real-time performance and fast algorithms. We have to deal with the safety issues, obstacle avoidance in brain navigation. We want to reduce the cost and achieve affordability to generate compact and lightweight AUVs. For AI and vision perception, low-level tasks include, for example, image enhancement, underwater segmentation for scene understanding, object detection and tracking, depth estimation for navigation, multimode sensitive fusion, HCI for pose, motion, and behavior understanding, deep learning network compression, few shots, and lifelong learning. For high-level tasks includes localization and underwater SLAM, path planning, navigation, obstacle avoidance, curiosity exploration, and multitask location, interaction, and cooperation between a group of AUVs. We are currently working on a smart AUV project funded by the EPSRC and industry partner. The aim is to develop real-time AI and vision-based autonomy to deploy on embedded devices on portable AUV. For many vision tasks, deep learning-based solutions are most promising. However, for underwater, it is difficult to collect sufficient data for deep learning. There's also color distortion problem. The color appears differently at different water depths, as you can see from this image. We have limited types of vision sensors to be used in underwater. We need also consider the experiment cost and safety issues when we develop the AUV. To solve this problem, we developed the two experimental platforms. One is a simulation-based, one is a real-world experimental platform. We use Unreal to simulate underwater environment, and we use the MATLAB Simulink to implement a simulated vehicle, including the motor control, IMU sensor, and also the 3D wave dynamic. Using the underwater simulator and the water camera, we can easily get sufficient images for deep learning model training. This allows us to use less real-world images to fine-tune the model. We can carry out physical testing in the simulation before testing in the sea. For real-world testing, we just replace the simulated AUV with the real AUV attached with cameras. The overall system communication is based on roles. Several software can be used to generate a simulation environment, for example, the Gazebo and the UWSV. We choose to use Unreal Engine because it provides us photorealistic images. Using Unreal CV, we can capture the RGB, depths, and normal images. We can also automatically generate the mask images for each of the objects, and we can use these mask images as a label data for segmentation on the deep learning. This is the 3D simulation of underwater environment generated by our industry partner for this project. Very realistic rocks, seagrasses, surface water dynamic, the top-down view, different camera views, large landscape, different patterns on the seabed, lighting effect, moving light patterns on the sea bottom, different underwater plants, lighting. It's a plastic object which we can use for detection for the environment protection. We also include some simple shapes generated by using the 3D scan and the photorealistic images. We can also control the light intensity at different depths and then provide the foggy effect. So this is the shape. And so the moving fish. For many underwater tasks, first we need to recognize different objects. We have tested on many state-of-the-art deep learning models. For example, the ResNet, ULU, FastRCN, and SSD. We have also developed our own compact real-time small models which can be deployed on the embedded system. Basic method is we use the pre-trained model on large public dataset like a Kuko or ImageNet. And then we can fine-tune the model with underwater images. We train the model using a large dataset developed from the YouTube videos, public dataset, and also our own recording. So the model can detect divers and many underwater animals. For example, the crabs, starfish, jellyfish, shrimp, shark, etc. Object detection with bumping boats is not enough sometimes. So we also need to know pixel by pixel location of the object for navigation. To train a deep learning segmentation model, we require the benchmark, labeled benchmark. To generate the benchmark, in our simulation system, the idea is we put the object in turn on the background image, and then we use this view to subtract the background. So we can automatically generate the masks for each of the objects for deep learning segmentation model training. To get the accurate segmentation model, we use the simulation image to pre-train the model. And then we can use limited real image from underwater to improve this model. This is the robot we used for experiment. Cameras are attached on the robot. We developed the deep learning-based AI vision algorithm. So this is the scene understanding. We segment different scene objects, grass, rocks, sand, and water. Fish detection, even very small fish. And also the diver detection. So the robot can track and then follow the diver to keep them safe. So AUV can help Seagrass survey for environment protection. So here is a public database we use to train our Seagrass segmentation model. So the first row, there's sampled images at different depths from 1 meter to 6 meters. And the second row is the from truth labels. The white area corresponds the non-grass, black indicates the grasses. So here you can see the changing grass shapes, texture, and color at different depths. And also the lighting condition largely change with increased depths. This is the compact model structure we developed for Seagrass segmentation. As you can see, the encoder we use backbone mobile net. It has 9 convolution layers, and encoder compressed the input image into multi-scale feature maps by downsampling. And the decoder has the compact 5 upsampling blocks. We also introduced escape connections, and these escape connections transmit low-level features extracted from the encoder to corresponding decoder blocks. Some of the results. The first column, they are the test sample image, and then the ground truth, the second column. Our result is in the third column. And also we compare our results with the several state-of-art UNet, Subnet, GCN, and DeepLab. So as you can see, we achieve a good accuracy. The reality is, it's easy to get images at high resolution and high quality from 0 to 2 meters from the seabed. The question is, can we train the model with these images? But we can also use this model to segment images from other depths, for example, 2 to 6 meters. So here, let's have a look at the result. So when we apply this model on 2 meters image, we achieved a similar accuracy with the state-of-the-art. But when we apply this model to 2 to 6 meters image, so as you can see here, we achieve the best compared to the other state-of-the-art. That means our model can better adapt to the different depths. Now let's have a look at the compactness and the speed of our model. The first row is our model, and we compare with our model with other 4 state-of-the-art. Overall performance, we achieved 200 frames per second, much better than others. For the parameters we used, is also the smallest, and also the computation cost calculated as blocks. We are the smallest. For the overall models, most of the parameters and the computation costs are spent on the encoder. For example, 64% the parameter on the encoder, and then nearly 70% on the calculation cost on the encoder. The decoder spends less. Let's look at the performance and energy cost on the embedded system, Jackson TX2. The first column is our model. We compare our model with the full state of art. So now you can see the overall network, the time spent on each image segmentation, the relative time in frame per second. Ours in red are always the best. For the network energy consumption, ours is always the lowest energy consumption. Color distortion is a problem for underwater images. As you can see from this image on the left column, the fish, the yellow isn't really yellow, and the white is not really white. It's kind of bluish. Yeah? So to solve this problem, we generate a GAN-based solution to transfer the blurry, foggy image into clear ones. Yeah? So this is some result on the left-hand side. Yeah, from the bluish image, and remove the color distortion noise and generate a well-balanced, white-balanced image. More examples of the results. On the left-hand side, these are bluish underwater image. And now with the GAN and enhancement, we can generate a much clear, better contrast and the white balanced image. So this way can help our segmentation or detection model to better detect objects or segment the scene. The first row shows the segmentation results on original image. The original image is kind of bluish. And the second row shows the segmentation results, improved accuracy on the enhanced image. This image is much sharper and good white balance. We deploy the vision AI models on embedded device on the robot. We choose to use Navida Jackson TX2 because it's high performance and also low power consumption. On the left-hand side is the control box. It includes the batteries, and Navida TX2, and the router. On the right-hand side is the underwater robot. In the front, we installed RGB cameras. And the image are taken and streamed onto the control box to process. And then the control command will sent back to the robot vehicle. This is the overall diagram of our onboard experiment. At this stage of development, we don't want to lose our robot. So we use a cable to connect the robot. The control box is actually on the boat at the sea surface. And the camera on the robot will take images and send the real-time video streams through the cable back to the control box on the boat. The TX2 and the control box will process the image data and other sensor data, and then send the navigation command and the control command back to the robot. The overall system communication is built on rows on each side, on the robot side and also on the control box. We have done many testings at beautiful Garda Lake in Italy. We used robots to carry out yellow ball or other object moving in the lake, and we used the AUV to detect and track the object. Here is the Loughborough research team working together with our industry partner in Italy. We first detect all the functions in the laboratory environment using a water tank to make sure everything is fine, working well. And then we carry out the onset experiment at the lake. So you can see the robot is not big, it's portable. One problem with the object recognition, detection, and tracking is the model will need to be pre-trained on the object. Otherwise, the model won't know any unknown or unseen object. So for AUA, one of the tasks is to explore. That means AUA needs to know some unknowns, unseen object. So abnormal detection for underwater curiosity is very important. So in this project, we developed some deep learning-based gun model to detect abnormal object. Let's have a look at the basic concept for abnormal detection gun-based deep learning structure. The model is trained with the noise input image, which only contains normal object. We have generator and discriminator in this network. Generator can only learn and reconstruct the normal object distribution from the input. It can't reproduce regions with unseen abnormal object. This will call the discriminator. Discriminator learns to accept the distribution from real image and reject the fake distribution from generated image. The network will generate probability matrix to classify image patches as known or unknown areas. So some results show here. The first column is the input image. They contain some unknown abnormal object. The first one, we can see this man-made structure or shape object. The second one has some shells in it. The second column is the generated image. Third column is filtered image. And the last column is the abnormal regions generated based on the probability matrix. Depth information is very important for AUV navigation and vision-based obstacle avoidance, but it's very difficult to get depth data. No reliable supervised information available for underwater environment. To solve this problem, we developed a self-supervised deep learning neural network for underwater depth estimation. The network contains the depth estimation part and also the camera pulse estimation network. Some result. Left-hand side is the underwater video with the schedule. The right-hand side is the depth estimation. So the result is quite promising, very informative for navigation purpose. A deep learning model usually has a very complex structure. This may reduce the real-time performance and require high computation power and memory. So we propose to use nature architecture searching and learning to find a compact structure without compromising the accuracy. The idea is to train a teacher network with complex structure, and then we can build a smaller student network by learning from the teacher. Using this method, we have saved 60% computation cost and still achieved the same level of accuracy. In summary, autonomous underwater vehicle is a challenging and exciting area. There are many open questions and problems. For example, the SLAM navigation and the localization for underwater reinforcement learning for robust control, lifelong active learning, high-level decision-making, and bio-inspired AUA, and also AUA swarm and task allocation, advanced manufacture and smart material. We expect step change in research and technology to bring large scale of adoption of AUA in many applications. I would like to thank our research team for their significant contributions, the PhD students and the postdoc doctors. I also want to thank our sponsor and our industry partner. Thank you very much for listening. Thank you for this opportunity. We would like to collaborate worldwide. Please do contact me for potential collaboration. Thank you.